Hi, and welcome back. This is lecture 2 of 3 on chapter 9 material. And in this lecture, I'm going to talk about uh, collisions that conserve energy, also known as elastic collisions. Now, this isn't going to be a terribly long video. And the reason why is because it's going to be pretty much jam-packed with derivation. So you may want to prepare. So what we're going to do is to work sort of a mock problem in which you have a mass sitting at the origin that is hit by another mass that's moving. And we're going to look at a before and after situation where before, at the origin, I'll say that you have mass m2 with an initial velocity of 0. Now, mass 1 here is moving to the right. It has a mass of m1 and an initial velocity that is not 0. I'm not going to give it a number, but I am going to note the fact that it is along the x direction. Okay? Now, in this example of an elastic collision, we're going to stay one-dimensional. In the next video I do, we're going to do 2 dimensions. So what's going to happen here is that mass 1 is going to hit mass 2. We're going to make the assumption that mass 1 is greater than mass 2. Okay? So if that's the case, if you think about your experience with colliding things, marbles against marbles, cue balls against pool balls, and whatever, the thing that has the most mass, if it hits the thing that's stationary, what's going to happen is mass 2 is going to be pushed to the right, while mass 1 continues to the right at a lower velocity. So we're going to have, in this particular example, m2 traveling to the right with a velocity of v2. But we also expect to see m1, because its mass is greater, traveling to the right as well with a velocity of v1. Now, what I want to do is to find v1 and v2, given this initial information, and also given the fact that this is a perfectly elastic collision. Now, perfectly elastic collisions conserve energy, which is a good thing, as we're going to see shortly. Now, so here, let's just look at our initial momentum. Our initial momentum would be the initial momentum of object 1 plus the initial momentum of object 2. And again, object 2's velocity is 0, which means that momentum is 0. Here, it's going to be m1 v1 naught x hat. Now, after the collision, if you look at our momentum, you're going to have the momentum of object 1 plus the momentum of object 2, m1 v1 x hat plus m2 v2 x hat. Now, conservation of momentum is going to hold. Again, we're dealing with a situation in which there aren't any external forces. So that means that my initial momentum and my final momentum are going to be the same. Or m1 v1 naught x hat is going to equal to m1 v1 x hat plus m2 v2 x hat. Now we can get rid of the x hats at this point. They cancel out. So what this does is to give us an equation that says m1 v1 naught is equal to M1 V1 plus M2 V2. All right, now, so remember what we're looking for is V1 and V2, but we have an issue. Unlike the previous examples that we've worked where we had perfectly inelastic collisions, in this situation, the velocities of these masses after the collision aren't the same, which means we have one equation and two things that we don't know. One equation and two unknowns means we can't solve this. So we need to appeal to something else to give us additional information. And that's where the fact that perfectly elastic collisions conserve energy comes in. Because not only is momentum conserved, but energy is conserved as well. So let's think about our initial energy. Our initial energy would be the initial kinetic energy of object 1 plus the initial kinetic energy of object 2. But if you take a look here, object 2 isn't moving, no kinetic energy, which means that our initial energy is just going to be 1 half m1 v1 naught squared. Now, after the collision, our energy is going to be in the kinetic energy of both of these masses. 1 half m1 v1 squared plus 1 half m2 v2 squared. So, as per conservation of energy, 1 half m1 v1 naught squared is equal to 1 half m1 v1 squared plus 1 half m1, or m2 rather, v2 squared. So this right here is an equation that relates initial stuff to v1 and v2, and then we have the one from conservation of momentum that says m1 v1 naught is equal to m1 v1 plus m2 v2. So now we have two equations and two unknowns. The issue that you have, though, is that this one's squared. So you have these squares on the v1 and v2. So how are we going to get around that? Well, we're going to take the same process that we normally do when we solve these sorts of things. We're going to solve for 1. We'll say we'll solve for v1, and then plug that into this equation right here every time we see a v1. So let me snag these two right here. I'm going to paste it right here. So these are the equations that we're working with. All right. So we have two equations and two unknowns, and we're going to solve this just like we do when we have situations like that. We're going to pick one of these to solve for and then plug it in to the other equation and then turn the crank until we can get this equation in terms of, we'll say, just V1 or V2, depending. So what I'm going to do is I'm going to work with this equation initially. So here's our equation, M1 V1 naught is equal to M1 V1 plus M2 V2. And I'm going to divide both sides by M1. So when I do that, I get V1 naught on the left-hand side. On the right-hand side, I get V1 plus M2 over M1 V2. So let me solve this for V1. And now what I'm going to do is to take, and every time I see V1 in this equation, plug this into it. So before I do that, I'm going to box this real quick because we're going to need this relationship whenever we find V2. So let's take this equation right here. Let's start working with it. There's a half in front of these guys, so that goes away. I'm going to also go ahead and divide through by M1. When I do that, this goes away, and you get an M1 under here. Looks looks like that. Now, let's plug this into this. So you got to square it, and then you have this at the end. Now let's use FOIL. First, outside and inside. Oh. Then last. And then you have the last term right here. Okay, so that's the result of your FOIL. And so the first thing I see is that this right here and this right here are going to cancel with each other. Now let me arrange this a little differently. Let's just sort of rewrite this. That's this term plus that's this term, and then we have this on the end. And that's going to equal to 0. So we got all three terms that are left over. Now, there's a lot going on here that's in common. For example, I see a V2 here, a V2 here, a V2 here. So if I divide through by V2, that's going to get rid of those. Each one of these has an M2 in it. This has two of them. So that's going to go away, that's going to go away, that's going to get rid of one of those. So what I have here is M2 over M1, V2 plus V2 minus 2 times V1 naught is equal to 0. So let me group these V2s together. You get that. I'm going to move this to the right-hand side. You get that. Now I'm going to divide both sides by this right here. Now, typically what we do next is to multiply this by 1 in the form of M1 over M1. And what that does is to put an M1 here, but then you have this that goes through, gets rid of this in the denominator, and puts an M1 right here. So if you do that, you get 2 M1 V1 naught divided by M1 plus M2. All right, so this is V2 right here. So let's write this up over here. So here we have V2 in terms of things that we know at the beginning of the problem, like the masses and the initial velocity. We still need to massage this in a form that works, because this has got V2 in it. So let's go ahead and plug V2 into this. I'm going to do that over here. So V1 is equal to V1 naught, that's coming from this, minus M2 over M1 times V2. Now V2 is 2M1 V1 naught divided by M1 plus M2. All right. Now, you'll notice here that the M1s cancel out. That puts an M2 here. Now, so we're almost done here. We still need to clean this thing up a little bit. And to clean it up, I'm going to multiply this by 1 in the form of M1 plus M2 over M1 plus M2. So that would make the right-hand side of this be equal to V1 naught times M1 plus M2 divided by M1 plus M2 minus 2 M2 V1 naught divided by M1 plus M2. Now what's going to happen here is this V1 naught is going to go through. You'll have a plus M2 V1 naught, a minus 2 M2 V1 naught. And this is going to combine to make this a 1, a negative 1. So your V1 naught, or V1 rather, is going to actually look like M1 minus M2 V1 naught divided by M1 plus M2. And there you go. You have two equations that give you the final velocities of these things, presuming you know all this initial stuff. Now, I want to be very clear about the conditions under which these were derived. Okay, let me snag them real quick. So here's our equations that we came up with. And here's the problem. Let me snag this too. Make sure I get everything here. At least everything here that's worth getting for my purposes. Okay, so here's our problem, right? Let me clear this up just a little bit. So this is the important condition that I'd like to draw your attention to. M1 is greater than M2. Okay, so what that means is that we're assuming after the collision, both M1 and M2 have velocities that are positive. And that's the assumption that we made when we wrote out our conservation of momentum. We put in positives. Now, it very well could be, for example, that M2's mass is much, much greater than M1. Okay? Now, in a situation like that, if I were to go over here and look at a situation in which M2 is greater than M1, let's take a look at the equations. Does that affect V2? No. Okay. You're going to end up with a positive number here no matter what, presuming that V1 naught's to the right. But look at what's going on with V1 now. V1, remember, is the velocity of our first mass, the one that's moving after the collision. If M2 is bigger than M1, then when you do the subtraction, you get a negative sign. So what that means is that V2 is going to continue off to the right like we expect. But object 1 is going to bounce off to the left. So if you're going to use these equations, be aware of that. Okay. Now, likewise, that makes sense if you think about it. Okay, that makes sense. From my experience, if you take something that's nice and heavy and you collide it with something that has a lower mass, then the thing that's got the lower mass does in fact bounce off. And the thing that has the biggest mass or the bigger mass does in fact move away. Okay? But what if the masses are equal? Okay? What if the masses are equal? Now, my experience when I was growing up, I used to shoot a lot of pool. Okay? And so if you didn't have any quarters for the machine, typically what I would do is I would just take the cue balls and shoot the cue balls. Okay, now cue balls have the same mass. In fact, that's how they know, at least how a pool table knows to sort a cue ball differently than it does the regular standard pool balls. And that's because the pool balls have masses that are just a little bit less than the cue ball. There's actually a cantilever system in the inside that is counterbalanced exactly to take and shoot the cue ball out, but let the others roll by. Okay. Now, so if you've ever shot a cue ball against a cue ball, or just a standard pool ball against a standard pool ball, and you didn't use any English at all. You didn't put the cue stick at the top to make it go faster. You didn't put the cue stick at the bottom to make it spin a little bit, maybe, or to the side to give it some side English. You shoot it dead on. Then what happens is when it hits it, this guy goes and this one stops. They exchange places basically. So let's see if that bears out if M1 is equal to M2. Okay, so if the masses are equal, then let's look at object 2's velocity. M1 would equal to M2, which means that here, this would be the same thing as basically 2M1. You'd have 2M1 on the bottom. You have, a 2M1 on the top. They cancel. And what that means is that object 2's velocity would be the same as object 1's initial velocity. But look at what happens to V1. The masses are the same. So when you do subtraction, you get 0. So object 1 stops and object 2 continues away at the same velocity that object 1 had. So like I said, they switch places. So as long as you're aware of the conditions under which we derive this thing, you can work with it. So you know what to do when you have, for example, or what to expect rather, when you have, for example, a large M2, if you will, or a large M1, or the masses are the same. All right. Now that said, let's just work a simple example here. You have a cue ball that has a mass of 0.17 kilograms. It's traveling at 5.5 meters per second when it collides head-on with an 8 ball at rest. If the 8 ball has a mass of 0.16 kilograms, what's the velocity of both the balls after the collision? Well, what I'm going to do is to basically snag all of this and paste it right on the next page, because this is what we need. So let's copy it. We'll paste it here. Okay, there's our equations. Let's just do a little bit of spring cleaning here. All right. So here's what I have. What I've been given is that M1, which is the mass that's coming in, that's the cue ball, is 0.17 kilograms. M2 is the 8 ball that's at rest. That's 0.16 kilograms. See, like I said, the masses are different. Okay. Now, we also know that the initial velocity of mass 1 is 5.5 meters per second in the x-hat direction as drawn. We know that the initial velocity of the second mass is 0. Okay? So what we're trying to find here are the velocities after collision. So here, M1 is greater than M2. Now, if you remember, those were the conditions under which we derived this stuff initially, which means that as we expect from our understanding, both V1 and V2 are going to be positive when we do this. And now let's just plug stuff in. V1 is going to equal to M1 minus M2, 0.17 kilograms minus 0.16 kilograms times V1 naught. V1 naught's 5.5 meters per second. And then we have to divide it by 0.17 kilograms plus 0.16 kilograms. So let's see what I get there. My calculator. So 0.17 minus 0.16 times 5.5 divided by 0.17 plus 0.16. I get a velocity after the collision of about 0.17 meters per second. Okay. Now, so what about for the 8 ball, which is M2? For the 8 ball, that's going to be 2 times M1 V1 naught. M1 is 0.17 kilograms. V1 naught is 5.5 meters per second. And then we'd have to divide by the sum of the masses. And if I do that, I get about 5.7 meters per second. Okay, so there you go. What's object 1's velocity? 0.17 meters per second, x hat. What's object 2's velocity? 5.7 meters per second, x hat. Okay? Now, so one of the other conditions under which we derive this was that M2 is at rest. What if they're both moving? Okay, so there is something that you can do when you have both of your masses moving before the collision. For example, what if I had a situation like this? Maybe this is M1 moving this way, has an initial velocity of whatever. This one right here is M2 moving this way. It has an initial velocity of whatever. I'll tell you what, let's just go ahead and put numbers in here so it's a little bit less abstract. V1 naught, I don't know. 2 meters per second x hat. V2 naught, I don't know. 6 meters per second x hat negative. Well, what you generally want to do in a situation like this is to make this problem look like a problem where M2 is at rest. So what I would do would be, before I worked it, to add. I want to add 6 meters per second x hat to both sides. Now, that doesn't affect the problem as worked, okay? Because what you're going to do is, if you were to add this to both sides, that would turn this into a problem that looks like M2 being at rest, because V2 naught plus V naught is 0 in this case. 6 plus minus 6. And now M1 is moving with a velocity, I'll call it V1 naught new, of 2 meters per second x hat plus 6, or 8. So what you do is you work the problem in this frame. What we've done is we've changed frames of reference. You work the problem in this frame, and then once you, in this particular frame, get V2 and V1 as vectors, you subtract away the 6 meters per second. So you add it at the beginning to solve the problem, and then you subtract it away, and you will get the correct answer. Okay, so the procedure that you have here is to put one mass at rest, by adding velocity to it, and then work the problem, and then transform back transform back to original frame by subtracting the mass, or subtracting the velocity rather. Okay, so this is the end of video 2. And in the next video, I'm going to show you how to deal with situations in which you have two-dimensional collision problems. It's actually a lot easier because now having two directions, you have two equations. You don't necessarily have to appeal to conservation of energy. And I'll see you then.